Okay. Hello everyone. Thank you for joining the talk today. Uh, Let me briefly introduce myself. My name is Yu Yan. I'm currently a PhD student at Nanjing University in China. It's a great pleasure to have this opportunity to share our recent research with you. Today, I'm going to talk about some of our recent progresses in online learning, which are published in Europe's 2023 and Europe's 2024, and I believe is a meaningful contribution to this field. These are joint works with Professor Zhihua Zhou and Professor Peng Zhao. We are now in the era of big data where machine learning needs to and inevitably has to deal with massive amounts of data. The left figure shows the relationship between the model performance and data size. Clearly, as the amount of data increases, model performance improves significantly, though we do eventually reach a plateau. This illustrates an important point that more data generally leads to better performance, although up to a point. The red figure shows the estimated global data volume growth from 2010 to 2025. The curve is exponential, so we are seeing a massive surge in the amount of data being created every year. In fact, by 2025, global data volume is expected to reach hundreds of zettabytes. And in the era of big data, we think online learning is essential. To see this, we can see that in today's world, we are dealing with an ever-growing amount of data, especially in the era of big data. One of the key challenges we face is how to efficiently process and learn from this data as it continuously flows. Big data arrives continuously, unlike static data sets that we might have worked with in the past. Today's data is continuously streaming in second by second. It's not just stored in large batches, but rather is dynamic and ever-changing, making it hard to handle with traditional methods. The second point is retraining from scratch is inefficient. With batch learning, we would traditionally wait for a large set of data to accumulate before we retrain our models. This process is slow and does not align with the real-time needs of many real-time modern applications. By the time the model is retrained, the data may already be outdated, resulting in efficient use of time and resources. On the other hand, online learning enables real-time updates. It allows models to adapt to on the fly with minimum delay. It can continuously learn from new data as it arrives, making it more efficient and suitable for dynamic environments. This is why online learning is critical in addressing the needs of today's data-driven world. In summary, online learning helps to keep models relevant and up to date, ensuring that they remain effective even as new data streaming continuously. Online learning is a process where the model continuously learns and adapts as new data arrives. Let me walk you through how it works. At each round, there are total, we can say capital T rounds. At each round, for example, in the Tth round, the learner first selects a point, or you can say an online model from a set of possible options or a set of some feasible domains. Uh, Meanwhile, the environment selects an evaluation function, or we call it an online function, to access how well the model is performing based on the chosen online model. Afterwards, the learner experiences a loss, FTWT, based on the evaluation function and observes some feedback about it, which helps get the model's future updates. We can formalize the online learning from the perspective of online classification. For example, in this setting, we assume that we are given a fixed classification loss denoted by L. At each round, we receive a data point with feature X and label Y, feature XT and label YT. Our model is represented by called a hypothesis function H, which is parametered by W. Given the data point, the loss incurred by the model is fully determined by the current model parameter, W. So here we can treat W as a decision variable, while the rest, including the loss function L and the data point XT, YT, can be seen as composing the online function loss function FT. In this way, the structure of online learning problem becomes clear. That is, the environment provides a new data point at each step, and we update our online model W accordingly. To make this concept clearer, let's look at a couple of examples. The first is spam filtering. In spam filtering, the system learns to classify emails as either spam or not. The classifier, which is the core of the system, selects a weight vector. This is a very simple example just for illustration, which represents the model's current understanding of the spam. Next, for each email, the system makes a prediction based on the features of the email, such as certain keywords or patterns. The prediction is compared with the true label of whether it's spam or not. If the model makes an incorrect prediction, a loss is calculated based on how far off the prediction was from the true label. Then the model updates its weight vector to improve these future predictions. The second example is online recommendations, such as the one used by streaming service to suggest movies or songs. Similar to spam filtering, the recommendation system constantly updates its model based on new data. However, instead of emails, the data might include user performance, user preference, viewing history, or other factors. At each time period, the system uses the most recent data to train the model and updates its parameters. The updated model is then used to generate recommendations for users. This cycle continues well with the system learning from new data and improving the quality of the recommendations over time. Now let's explore a more formalized problem setup named online convex optimization, or short as OCO. Is particularly useful where the learner's goal is to minimize a convex loss function. The protocol is almost the same as that of the online learning that we have introduced in the last slide. It also continues for capital T rounds, and inside each round, for example, the T round, the learner submits an online model XT. We call it XT here, and from now on, simultaneously the environment decides the convex loss function FT. Then the learner suffers FTXT and receives some gradient information of the loss function for its future updates. In the online learning, the fundamental goal is we aim to make the online prediction as good as the best offline model. What does it mean? A fundamental performance measure in online learning is called the regret, which is a relative benchmark between the online model and an offline model. The online model is measured by its cumulative loss, and the best offline model it would have made the best predictions if it had known all the data ahead of time. Now let's talk about universal online learning, which extends the idea of online learning to consider different types of curvatures in online loss functions. The most general function class is convex functions, which contains lots of functions of interest. Another type of function that is quite familiar to maybe many of us is a strongly convex loss, such as a squared loss. From a mathematical perspective, in addition to the linear term that comes with convex functions, a strongly convex function has an additional squared penalty term, a negative squared penalty term. Intuitively, this additional negative term helps to create a stronger curvature, which can provide a better guarantee for a smaller regret bound. There is also another kind of function class which we call alpha exponential concave function. This kind of function lies between convex and strongly convex functions. It also includes a wide range of functions such as logistic loss. For example, intuitively, we can think of exponential concavity as having strong convexity in a specific direction of the gradient. This means that in certain cases, the function behaves somehow similarly to a strongly convex function, but it may not hold this property everywhere. In universal online learning, the type of as we have shown before, the type of functional curvature plays a crucial role in determining the best possible regret bounds. The curvature essentially influences how quickly the model can adapt and how efficiently it can minimize the loss over time. For example, for convex functions, the typical algorithm is online gradient descent. The regret for convex functions is about the square root of the total number of rounds, capital T. And for strongly convex functions, the best algorithm is still online gradient descent, but with a slightly different learning rate. And the optimal regret bound is log T over lambda, where lambda is the coefficient of the strong convexity. Finally, for experimental concave functions, the best algorithm is online Newton step. The best and optimal regret for this type is also log in T, but with an additional dimension dependency D. In summary, the curvature of online function plays an important role in determining the best achievable regret, and the algorithm must adapt accordingly for each step to ensure the optimal learning and convergence. Uh, but we can notice that common algorithms are typically designed to work well for only one specific type of curvature. But what if the curvature type or maybe its coefficient is unknown to us? In this talk, we will focus on universal online learning where the curvature is not predetermined, and we need to find ways to adapt it to any type of curvature in the learning process. Does anyone have any questions? You can open your mic directly or drop a message in the chat room. In the next, we will provide a more formal definition of universal online learning. Specifically, universal online learning aims to design an online learning algorithm denoted by script A, which is on the left-hand side of the equation, and we want to make it to behave in the following way. When the online functions are convex, that is the third line. The regret bound achieved by script A is the same as the one from an algorithm specifically designed to optimize convex functions. When the online functions are strongly convex, script A can achieve the same regret bound as an algorithm tailored for strongly convex functions. Similarly, for other types of functions, not just experimental concave functions, the regret bounds will be equivalent to those from algorithms optimized for those specific types. Additionally, another keyword in the title of our talk is gradient variation. So what is called a gradient variation? To introduce the gradient variation, we first introduce the notion of problem-dependent regret. We can notice that some of the regret bounds we introduced before are only measured by the total number of rounds, capital T. This only represents a worst-case theoretical guarantee, which does not adapt to the difficulty of the online learning problem itself. So a natural question is, can we exploit the niceness of the environment for improved result? In this talk, we focus on a theoretical guarantee based on what is called the gradient variation. This quantity measures the cumulative change of the online functions at the gradient level. While in the worst case, it is still in the order of t, but in some simpler case, for example, the online function sequence is not very non-stationary, or you can say is almost stationary. This kind of gradient variation can be significantly smaller than the order of t. This allows the online learning algorithm to adapt to the difficulty of the problem itself. For example, if we, in the worst case, for strongly convex functions, we can obtain a log t over lambda regret. In the problem-dependent regret, what we want to achieve is a log Vt over lambda regret, where Vt can safeguard the best case of t, but it can be smaller in some easier online learning problems. Although the gradient variation measures the degree although it only measures the degree from its definition, only the degree of the change in the gradients, it can be directly used to derive other types of problem-dependent quantities in analysis, such as other widely used problem-dependent quantities in the online learning literature, such as small loss or gradient variance. This means that the regret bound based on gradient variation not only captures the variation of gradients, but also other perspectives of the difficulties of the online learning problem. This can provide a more comprehensive understanding of how the problem behaves. Besides that, the gradient variation has several other applications. Recent research has shown that it can be used to bridge stochastic and adversarial online learning. Additionally, gradient variation plays an important role in achieving faster rates in games. Moreover, gradient variation in online learning can be also used to achieve convergence rates, accelerated convergence rates similar to Nestrov's accelerated method in the offline convex optimization. We will introduce the third and second application, but omit the last one. Before presenting our results, let's first provide a general framework to solve this problem. In short, what we want to do in general is to handle the uncertainty of the environments. To address the uncertainty, we leverage the classic idea of ensemble from machine learning. Besides, since we are dealing with an online problem, we designed an online ensemble framework. Specifically, we use a series of base learners to explore the uncertainty of the online functions since we do not know the curvature of the online functions. More specifically, base learners are designed to guess the curvature types or its coefficient. To see this, for example, for convex functions, we run online algorithm designed to optimize convex functions. For alpha exponential concave functions, we can use a set of base learners to optimize these functions. This set of base learner all runs the algorithm for exponential concave functions, but why do we need multiple base learners in this small group? Is that the coefficient of exponential concavity alpha is also unknown, so we employ multiple base learners to guess the potential values of alpha. The same approach often applies to the strongly convex functions. On top of this, we run a meta learner to weigh the decisions of the base learners. That is, we denoted by XTI the decision of the ith base learner, and the meta learner will give it a weight PTI and submit the final decision XTI, the weighted combination of all base learners' decisions. The meta learner can learn its weights in the learning process so that it can adapt to the best base learner in the learning process. In our first work, we present a universal online learning algorithm with near optimal universal gradient variation regret. Specifically, under standard assumptions, our algorithm is able to achieve that when the online functions are lambda strongly convex, we can achieve the optimal log VT over lambda. When the online functions are alpha exponential concave, we can achieve the optimal D log VT over alpha. But when the online functions are convex, we can achieve a square root of VT times log VT. Notice that the third result is not strictly optimal since the optimal result is square root of VT. We only achieved a near optimal rate with an additional log VT factor. To further improve this result, in our second work, we present a universal online learning algorithm with the optimal regret bounds. Compared with our first work, we have made improvements in the result. We have not only maintained the optimal regret bounds for exponential concave and strong convex functions, but also for convex functions with square root of VT. This means that for the three common types of online functions in online learning, we can now achieve the optimal gradient variation regret bound using a single algorithm. Comparing our two works, although the result of the NeurIPS 2024 work exceeded exceeds the result of the last work. It does not mean that the second work is strictly optimal. The first work has an important property called RVU, which stands for regret bounded by variation in utilities. This property is crucial for achieving faster rates in games, as we will show in the next slide, and we will discuss the significance of both results and their importance in the upcoming applications. Next, we explore two applications to demonstrate the effectiveness of our method. The first application is a two-player zero-sum game, with a simple example being the game of rock, paper, scissors. In this game, there are two players, which we refer to as X player and Y player. Each player provides a mixed strategy over the action set. In this application, we aim to solve a classic game theory metric called the Nash equilibrium. A Nash equilibrium is a stable state where no player wants to deviate from their current strategy. Directly solving for Nash equilibrium is challenging, so instead, we often use iterative methods to approximate it, known as repeated play. We model this as an online game protocol. Specifically, in each round, the X player and the Y player submits their strategies called XT and YT. The unknown payoff matrix A determines the loss for XT, which is XT transpose AYT, and the same reward for the Y player, because this is a zero-sum game, and both players receive gradient information to update their strategies. For example, the gradient of X player is AYT, and the gradient of Y player is AXT. RVU is a key property in achieving the faster rates in games. For example, if the X player uses online learning algorithms that optimize for gradient variation, we can derive a regret bound that reflects this kind of adaptivity. In that bound, the regret of X player can be bounded by several terms. The first term is a constant, and the second term, the blue term, captures the gradient variation of the X player. Since the X player's gradient depends on the actions of the Y player, this term essentially reflects the stability of the Y player. At the same time, the red term, the third term, represents the negative stability of the X player's own strategy XT sequence. Although these two terms do not directly cancel out, something interesting happens if we also write out the gradient variation-based regret for the Y player. We can find that in the X players and Y players bound, these two bounds can partially cancel each other out, with which can upper bound the total regret, the regret summation of X and Y, by a constant. This is a much stronger guarantee than the typical square root of T style regret bounds in the adversarial setting, due to some specific structure of the game, and it demonstrates the real power of RVU-based analysis in the game theoretical learning. The RVU property is essentially you can also call it a gradient variation bound. So this is why we study gradient variation bound. One of the key reasons is that it plays an important role in achieving the fast rates in game theory. Why do we care about regret summation? This is because regret summation is often closely related to some global performance measures in games. For example, it's directly related to metrics like Nash equilibrium regret and the duality gap. These measures help us to understand how well both players are performing over and whether their joint strategies are approaching the underlying Nash equilibrium. Just to evaluate the effectiveness of our method, we designed a synthetic but some kind of artificial game scenario. Specifically, we consider a min-max optimization problem, or you can call it a saddle point optimization problem, where the function is convex in X and concave in Y. To demonstrate the universality of our method, we allow the function f to take two possible forms, that it can be either bilinear or strongly convex, strongly concave, but we do not know which one it belongs to. These two kind of loss functions are similar to the optimization of strongly convex or convex functions in the OCO setup. In addition, to highlight the RVU property of our algorithm, we consider two types of relationships between players. The first is honest case, where both players use the same online learning algorithm or similar online learning algorithms. In this setting, we can directly benefit from the RVU property as shown in the last slide, which leads to the cancellation effect I mentioned earlier, allowing us to achieve a constant regress sum. The second is the dishonest case, where one player may not follow the agreed protocol. This situation essentially degenerates into two separate adversarial online convex optimization problems. Since we are considering two independent aspects, including the structure of the function f and the honesty of the players, and each aspect has two possibilities, which means our algorithm needs to be robust to all four combinations. And here are our result. In the honest case, regardless of whether f is bilinear or strongly convex, strongly concave, we can always obtain a constant regress sum. This is mainly due to the RVU property, or you can call it the gradient variation regret. And in the dishonest case, if the function is bilinear, we can get a square of t, near optimal square of t regret bound up to log factors, which coincide with the square of t regret for convex functions in the adversarial setup. And if the function is strongly convex, strongly concave, we achieve a log t regret, which coincides with the same log t regret for strongly convex functions in the adversarial setup. Now we introduce the second application of our method, which we call stochastically extended adversarial. By seeing this, the name of this problem, you can see that it consists of two parts: the stochastic optimization and the adversarial optimization. This setting focuses on how the online function can be generated. If each online function is generated by randomly sampling from some distribution, we are in the stochastic online convex optimization setup. On the other hand, if the functions are generated in a worst case manner by an adversary, we call that adversarial online convex optimization. Traditionally, these two lines of research were studied separately. However, a recent study published in Europe's 2022 revealed the key role of gradient variation and showed that there is actually a natural interpolation between the stochastic and adversarial setting. To formalize this, we assume that each loss function f is sampled from a distribution called script ft, and we can define an expected function over this distribution denoted by capital Ft. Now the gradient variation between ft and ft minus 1 can be actually decomposed into three terms. The first and third term reflect the randomness introduced by sampling ft or ft minus 1 from capital Ft or capital Ft minus 1. This represents the stochastic variation, or you can call the noise in stochastic optimization. The middle term captures the change between the expected function, the capital Ft and capital Ft minus 1, which reflects the actual adversarial variation between rounds. This decomposition helps us better understand the structure of the problem and bridge the gap between stochastic and adversarial settings. Here we formalize the two kinds of variation, which are stochastic variation and adversarial variation we just introduced using precise mathematical notations. We define the stochastic variation as the expected difference between the gradient of a sampled function f and its expectation capital F, and the adversarial variation as a change in the expected function's gradient across time. Now the key takeaway message here is we can using our universal online learning with gradient variation technique, we can use just a single algorithm to obtain regret bounds for all three types of functions, including convex, strongly convex, and exponential concave functions in the SEA setting. And what's more important is that these regret bounds are tight. In purely stochastic and purely adversarial settings, our result can recover the state-of-the-art bounds known in these individual settings. So despite the case we are working with an interpolated setting where both types of the variation are present, our algorithm adapts naturally and matches the best known performance in each case, all without needing to know whether the environment is stochastic, adversarial, or somewhere in between in advance. Next, we briefly introduce the core technique behind our solution. To see this, since we adopt an online learning framework, we can also decompose the regret in a similar way into the meta regret and the base regret. More specifically, in this equation, the first and the last term appears in the definition of regret, and we insert an additional term, ftxti star, which is a cumulative loss of the best base learner whose index we denoted by I star, to split the total regret into two parts. The first part we call it a meta regret, and the second part we call it a base regret. Here the I star represents the best base learner. The best base learner is the one that with the right guess of the curvature type and the closest guess of the curvature coefficient. In this decomposition, the base regret measures the regret of the best base learner. In other words, the base regret is the best achievable performance if we would have known the true curvature and its coefficient in advance. And the meta regret reflects the ability of the meta learner to track the best base learner over time. And importantly, I want to emphasize that the meta learner does not need to know which base learner is optimal. It just needs to learn to adapt to the best base learner over time. The base regret is still an OCO problem, so we focus on how to optimize the meta regret. To optimize the meta regret, we reduce it to a classic framework in online learning known as prediction with expert advice, or short as PEA. Since the final decision XT is a weighted combination of base learners' outputs, we can use convexity to upper bound FTXT by the weighted sum of base learners' individual loss. The base learner's individual loss is denoted by FTXTI. By defining XXTI as a loss incurred by the S expert, that is the S base learner, the meta regret naturally becomes a standard PA problem where the goal is to compete with the best expert, which refers to the best base learner in our setup. Now let's talk about the technical challenge in solving this problem. Recall that the definition of gradient variation measures the maximum change in gradients between the consecutive rounds. However, in practice, we can only query the gradient at the single point xt in round t. As a result, we can only estimate the gradient variation based on these observed points, leading to what we call an empirical version of the gradient variation. Therefore, an important technical challenge is to bridge the gap between the true gradient variation and the empirical gradient variation we actually observe in the algorithm. In this talk, we introduce our two works, each addressing this challenge using a different technical route. The first approach tackles this problem by inserting an intermediate term that we call the gradient of ft-1 of xt into the empirical gradient variation expressions. Then, by leveraging the smoothness of the online functions, we can decompose the empirical gradient variation into two terms. The first term corresponds to the true gradient variation, which is what we ultimately want. And the second term captures the stability of the algorithm, that is xt minus 1. That is how much the iterates xt change over time. The main challenge is the point xt is a weighted combination of base learners' decisions, since we are using a two-layer online ensemble framework. So if we want to control the difference between xt and xt-1, we cannot just analyze the base learners in isolation. We need some kind of collaboration between the meta learner and all base learners. To control the stability of the overall algorithm, we further decompose it into two components. The first is the stability of the first term PT is the weight of the meta learner. PT minus 1 is the stability of the meta learner. And the second term is a weighted combination of base learner stability xti minus xt minus 1i. The first part, controlling this part requires the meta-based, controlling the second part requires meta-based collaboration. The first part, the stability of the meta learner can be handled if we using certain kinds of meta learning algorithms. So it's some standard technique, and we can handle it easily. The main challenge is how to handle the second term, which involve both the decision of the meta learner and the decision of the base learner. And intuitively, it needs some kind of collaboration between the meta and base learner to cancel it. To handle the second term, we introduce the correction term into the meta regret. Specifically, recall that without any correction, our meta regret can be reduced to a standard prediction with expert advice PA problem, as we discussed earlier. Now, suppose we modify the PA problem by adding an additional correction term marked as CT to the loss vector LT. If we can still obtain an upper bound, let's call it X, capital X, for this corrected regret, then we can analyze the original uncorrected meta regret, whose loss vector is just LT, by moving some correction-related terms to the right-hand side of the inequality. What we get is that in addition to the original upper bound X, two new terms appear. The first is a negative term, which is a weighted combination of the correction terms across all base learners, and the positive term, which corresponds to the correction term for single base learner, specifically the one indexed by I star, which is a best base learning hindsight. If we set the correction term CTI to be the stability of base learner I, then the negative term exactly cancels out the weighted combination of base learner stability, which is hard to control, a hard to control part we were concerned about. Meanwhile, the remaining positive term is just the stability of the best base learner, which can be handled internally within that base learner using some standard techniques. The intuition behind this technique is that we add some corrections in the loss of the meta learner to punish less stable base learners. This is the last slide shows our first work. Our second work takes a completely different technical approach to handle the empirical gradient variation. The first key idea is to provide a tighter upper bound on the squared gradient variation. We focus on the squared gradient variation since the definition, due to the definition of the gradient variation you can see in the above. Instead of just using the standard smoothness assumption, which gives us a bound based on the square norm of xt minus 1, we leverage a more refined tool called the Bregman divergence. This is a useful property for smooth functions, and you can refer, for example, refer to Nestrov's convex optimization book for more details. Bregman divergence intuitively measures the gap between a convex function and its first-order linear approximation. Intuitively, it captures how nonlinear the function is between 2 points. For the squared gradient variation that we care about, using a Bregman divergence-based bound leads to a tighter and more precise control compared to the standard smoothness-based bound. This makes the analysis easier and more accurate intuitively. Based on this property, we propose a different decomposition of the empirical gradient variation that we have to deal with to obtain the true gradient variation. In particularly, we decompose it into 3 parts. The first part and the third part can be combined into a Bregman divergence term, and the rest term is the true gradient variation, that is the quantity that we ultimately want. The positive Bregman divergence term is measured between xt and x star, where x star is a comparator in the definition of regret, which is typically chosen as an optimal decision in hindsight. Thus, the last remaining thing is to cancel this positive Bregman divergence term. And how to cancel it is very simple. Notice that when we linearize, notice that the left-hand side is a definition of regret, and when dealing with the definition of regret, we usually first linearize it, which is the first term on the right-hand side, and discard the second term, which is a negative Bregman divergence term. That is to say, the Bregman divergence term naturally comes from the process when we linearize a convex loss. Since the linear functions are the hardest case in the convex optimization as they have the weakest convexity, this compensation, that is a negative Bregman divergence term, can be seen as some compensation of the linearization. And we can, this negative Bregman divergence term is totally algorithm independent. And we can use this negative term to cancel the positive Bregman divergence term that in the equation above. That's the main content of our two works. And let me give a brief summary here. To summarize this talk, we explored the problem of universal online learning with gradient variations, which aims to adapt to different curvature types of online functions and data difficulties in a unified way. To solve this problem, we introduced a general framework called online ensemble with adaptivity, allowing the learners to automatically adapt to the underlying structure of the online loss function, whether they are convex, strongly convex, and exponential concave. We demonstrated the effectiveness of our approach in two important applications. The first one is stochastic extended adversarial in the optimization field, and the second is online games. Our analysis briefly is built upon the meta-based regret decomposition, which separates the challenge of the learning from multiple-based learners from the regret of each base learner itself. Finally, we presented two technical approaches for achieving the gradient variation regret in the universality sense. The first one is based on correction terms for punishing less stable base learners, and the second one is mainly from some analytical techniques. Is based on the Bregman divergence, which acts as the Bregman divergence acts as some kind of compensation from linearization and allows tighter control of the gradient variation. And together, these techniques enable us to achieve the optimal gradient variation regret without knowing the curvature information of online functions in advance. Thank you much for your attention. That's the end of my talk, and I'm happy to take any questions. Please feel free to ask. You can also drop a message in the chat room.
Just feel free to answer any questions for that. Yeah. I see someone is raising their hands.
Yes, thanks for your presentation. I have a question about the setting of these works. As you said that the algorithm has no idea about the curvature of the functions, of the received functions, but I said that what you are going to introduce is full information setting. So as the algorithm knows the loss function, why they cannot acquire the curvature of the loss function? Could you please give a more emphasized explanation about this problem?
Okay, thanks for your question. It's a good question. Of course, it can require to know the curvature of the online functions. If we know the function, if we know the curvature, we can use a very simple algorithm such as online gradient descent to solve this problem. And what we want to handle the cases that maybe in some cases that we don't know the curvature of the online functions, or maybe in some problems, the curvature of the online functions may have several options, and we don't want to design many specific algorithms for these specific curvatures, and we want a unified algorithm to solve them all. And this is a key idea of universal online learning. And we believe that if, for example, in some real-world applications, if we can know the curvature of the online functions, we can use a much simpler algorithm to solve it directly.
Okay, thanks.
Thank you for question.
Sorry, I have questions regarding the cancellation effect you mentioned. I'm not really understand what do you mean when you say you have some cancellation effects. I mean, in the page of 19th.
Do you mean this page?
Yes, yes. You mentioned you mentioned some technical stuffs about uh cancellation effect. What do you mean when you say that in I mean in solving this problem?
Okay. As you can see, for example, let's look at the game protocol first. In this game protocol, there are two players, X player and Y player. And X player, the gradient of X player, since we are facing a full information setup, the gradient of the X player is AYT, and the gradient of Y player is AXT. And what we want to optimize, for example, the regret of the X player, if we use some kind of certain algorithm, for example, that algorithm called online mirror descent with last round gradient, we can obtain a regret bound in this form. This form contains three terms. The first is a constant, and the second term is a gradient variation. It's a gradient of variation of the X player. In the worst case, you can directly bound this term by the order of t, and maybe you can obtain a square of t regret ultimately if you choose some certain kind of step size. But in the setup of game theory, the gradient variation has some nice and more structured. It has more structure. For example, it contains the regret of the X player contains the gradient variation of YT. And on the other hand, if we use some kind of standard online learning techniques, the red term is a negative stability term. Although the red term cannot directly cancel the blue term, but if we also write out the regret bound of the Y player, you can see that the red term of the Y player can cancel the blue term of the X player. If the matrix A, the norm of the matrix A is bounded somehow, and the red term of the player X can cancel the blue term of the blue term of the player Y, and these four terms can cancel each other out, and make the regret summation to be bounded by the first two terms of the regret, which is a constant.
I see, I see. Thank you for your explanation. And I'm sorry that maybe I'm a newer, but I'm not really understanding your standard approach. I mean, you are solving a kind of universal online learning, right? And I saw that you proposed to have a weighted sum of the base learner in your first maybe in your
Yeah.
yeah I mean you are in my understanding, are you adjusting the PI to determine what's your confidence over the functional curvatures? Is that mean that the PI means some kind of confidence that um, the meta learner think what is the curvature of the functional behind?
Yes, you're right. If the weight pi of some specific I is large, it means that the meta learner think this kind of base learner is maybe with the most accurate guess of the curvature type of its coefficient, and it means that the meta learner gives more its weights to this base learner.
So uh, if the x if the underlying function is almost for example, is almost strong, is almost lambda strongly convex all the time, and will your so the PI will turns to be 1 over the, I mean, it will assign all of the weights to that to that learner that target at lambda strongly convex. Is that correct? I mean,
Yes, you are correct. Eventually, maybe.
okay, thank you. And I'm also curious about I mean the what do you say about the when you mentioned the sorry, I would like to remember maybe the last few slides. Maybe the you mentioned that you have some correction terms to cancel.
Do you
Yeah,
mean this?
yes. How to I'm not very grasp your idea. Can you explain more how to add the corrections to punish some less stable base learners? I don't get the general idea, sorry.
Okay, it's okay. First, the first equation above is what we decompose the stability of the overall x, which is we decompose the xt minus 1 into 2 parts. This decomposition is you can see in a black box analysis, and you can just remember it. And this decomposition consists of two terms. The first term is pt minus 1, which is pt is the weight of the meta learner, and this term can be handled inside the meta algorithm if we choose some certain kind of meta algorithm. And what is more challenging is the second term. You can see that it involves both the decision of the meta learner and the base learner. This is you can see this is some kind of weighted sum. The weight is PTI, and it combines the stability of the ice base learner. And how to cancel this term is that you can see that as we introduced before, we can optimize the meta regret as a PEA problem. And you can see the last equation of its form, where the loss vector is LT and the decision is PT. And here, we do not directly optimize the original LT, but we add an additional correction term, the vector CT, into the regret. If we can still obtain this corrected regret by a capital X, and for the true meta regret that we are concerned about, that is the one without CT. That is, we can move all the terms that is related to CT to the right-hand side of the inequality. That it contains the right hand of the inequality now consists of 3.3 terms. The first is the upper bound x, which is usually maybe a square root of VT or something else. And the second term is the most important term. That is, it is a negative term. Also, it is a negative stability. It is a negative some kind of weighted combination of CTI. CTI is a correction on the ice dimension. And by setting CTI to be XTI minus XT minus 1I, and you can directly use this the second blue term to cancel the second term in the first equation. And on the other hand, this correction also imports a positive term on the I star, on the dimension of I star. And this is only the stability of this only one base learner, and you can handle it inside this base learner directly. Do you get what I mean?
Oh, how the CTI start is designed?
You can see that if we do not give the specific formulation of CTI, the negative term is about PTI, CTI. But what we want is to cancel the second term in the first inequality, that is PTI. with times the stability of the I-space learner, that is the square norm of xti minus xt minus 1i. So we directly set CTI to be this term to cancel it. Do you get it?
Okay, so I may get a general idea, but do you have a formula of the CTI star? I mean,
CTI star is equals to the stability of the I-space learner, that is xt I star minus xt minus 1 I star, the square norm.
I see. Oh, I see.
Yeah.
Okay, that's interesting.
Okay, thank you for
For the page 28 to 29, if I memory well, yeah, yeah, you use the smoothness coefficients of fragment divergence to approach your to control the difference of the two VT, right?
Yes.
So,
Actually,
okay, so
yes.
yeah, yes.
Due to this property, this upper bound L times the Bregman divergence is smaller than if we directly use the smoothness assumption, that is square norm of xt minus 1. This term is smaller than this term, so we can use we can give it a tighter upper bound, and we can cancel it from some other methods. That's the brief idea.
Okay, I see. Okay, thank you.
Thank you for your question.
Okay, is there anyone have other questions? Just feel free to answer.
Yes. I also have some problems about you said the technical routine tool here, and as you say that this is about the Bregman divergence, but in the analyze, how can you skip to the case that about, for instance, some in the technical routine one's problems, like how to get the CT here, or you find a more refined bound.
Yes, the first observation is that we can upper bound the gradient variation. For example, in one round by a tighter, we give it a tighter upper bound.
Yes.
Compared with
But actually, you also need to consider like the weighted sum of each base algorithms, right?
No, this we do not need to cancel the weighted stability as introduced in the last paper. This is because we use a completely different decomposition of the empirical gradient variation here, and we decompose. You can see we decompose it into 3 terms, where XTI is compared in the definition of the regret, and the first term and the third term, we can use this definition to change it into a Bregman divergence related term. And these 2 terms only, you can say it only shifts by 1 time step, and you can actually combine them into 1. And the second term is exactly the true gradient variation that we want. And to control this term, to control the red term, the Bregman divergence term, we directly use some compensation from the when we want to linearize the convex function from the beginning. These 2 terms can directly cancel out, and we can have the final bound that depends on only the true gradient variation VT.
So actually here we need only to give the bound of the Bregman divergence of X star and XT, right?
Yes, the second method is very simple and elegant, I think.
Yes. And But is this Riemann divergence is related to, for instance, choosing the parameters of strongly convex functions and exponential concave functions? Right?
Maybe not actually. This you mean this negative fragment or this positive term?
I mean the negative part.
The negative term, as you can see, this equation, if we remove all the summation, all the summation operator, this equation is exactly the definition of Bregman divergence. So it since Bregman divergence, you can define it on convex functions. So this negative term appears in all kinds of convex functions optimization. So it also fits for experimental concave functions or strongly convex functions.
Okay, so so I also remember that you mentioned okay. So in this case, actually, what we are approaching is the algorithm actually approaching is selecting some parameter which is approaching the summation of the curvature of the simulative loss functions. Is this understanding correct?
Sorry, I did not quite get it.
Because in the algorithm, actually the expert advice is choosing some parameters of the curvature of the loss functions, right?
Yeah, yes.
So, but actually, it is just approaching the best suitable curvature of the loss functions, right?
Yeah, yes.
So in this case, I'm just have some worry that is the algorithm actually approaching the simulative optimal or the simulative approached converter of the algorithms.
Sorry, I did not still get your question. Do you are you referring to this page about the technical
No,
part?
not this page, but just your algorithm framework.
Okay, you mean this page?
Yes. Actually, you can say that in the expert advice, actually, the algorithm is choosing PT here.
Yeah.
And it is just choosing or approximating the best parameter in hindsight of the loss functions, right?
The meta learner choose a weight. The weight is, for example, the weight PTI is assigned to the ith base learner. During the learning process, it can, if some specific base learner I is strictly better than the other base learner, the PTI, the weight the meta learner assigned to it will become larger and larger in the learning process. Do you mean it?
Yes. So actually, it is actually approaching the best parameters for the base learners, right?
Yes.
So does that mean that all the loss functions is actually approaching by some, for instance, lambda j strongly convex functions?
Yes.
Then actually it is quite interesting that so the algorithm is approaching the best parameter or approaching the simulative optimal. I'm just thinking that it is a little bit
You
mixed.
mean the two goals seems to be a little.
Yes. What actually is the true goal is the algorithm.
You can see, let me you can see the meta-based regret decomposition.
Yes.
The meta learner is is doing what you just said. It want to approaching the best base learner, and the best base learner, the performance of the best base learner is measured by the regret that is compared with the best compared in hindsight. For example,
Yes.
if we are facing a lambda strongly convex function class, and the blue term is actually the base learner that runs the algorithm for strongly convex functions, and with the closest guess, maybe you can say you can think, for example, in the simplest case, it knows the best base learner is assumed to know that this function class is strongly convex and the value of lambda. And the blue term
Yes.
is actually log VT over lambda, which is the optimal rate for this problem. And in this case, the meta regret is actually a constant. And I do not introduce into this talk. And this is mainly because that when the functions are strongly convex, the meta learner is it brings great benefits to the meta regret optimization that in strongly convex case and the external concave case, the meta regret are actually a constant. And you can see when the meta regret is actually a constant, and the final regret can perfectly inherit the regret of the best base learner. And these two goals do not conflict. What we need to do is to perfectly control both terms to make the final.
Actually, I mean that for the meta regret here, it looks like just expert otherwise approaching, right?
Yes.
Actually, it's approaching the best one. But for this part, I think there is a lower bound for the expert advice. It must be square root of t, right?
The lower bound square root of t only holds for convex functions. For convex functions, we can actually bound this term. I got what you mean. 就是the lower bound for convex functions without smoothness is square root of t. And what we have, we are facing a convex and a smooth function here. So the lower bound is not square root of t.
Okay, so this part, it is possible that it could be
Yeah,
smaller.
for convex functions, we can bound the meta regret by square root of vt. And for external concave and strongly convex functions, we can upper bound the meta regret by only a constant.
Okay. And for
I think you can discuss these details maybe offline.
Okay.
And yeah, it's maybe there are some very technical parts of checking the proving details. Yes, I think maybe it is not quite clear to discuss it. Just talk online, and maybe you can discuss it later on. Yeah,
I would like to have your contact information, and if you have time, we could discuss it just after this talk. Is it available?
Yeah, of course. Just see the announcement of the in Doorkeeper, and you can have the abstract, the title abstract of this. Let me just Yu-Hu, can you share your homepage in the chat room?
Okay. Can I see it? I have sent my homepage website in the chat room.
And also, this is the announcement in Doorkeeper, and you can check all the details, the bio, the title, and abstract here. Yeah, you can just discuss it. Yeah, okay, there is a question in the chat room. Is this approach related to bandit problem?
Thank you for your question. We are facing a full information problem which means that you can actually get the gradient information of the online algorithm at the end of each run. I believe the bandit problem where you can only get one specific point value, function value, is much harder, and we are still working on it. Thank you for your question.
Yes. If you have any other questions, just feel free to write down in the chat room. It's fine, and also speak up. Yeah.
I have an additional question. Is your approach, in my understanding, the convex or strongly convex is the F with regard to the X, right? The X is somewhat like a decision or somewhat like a learner. So, but in my understanding of your PowerPoint, it seems that the X need to be how to say? In my understanding, because when you talk about the implication of online learning at the start of your talk, you mentioned the learning, right? I mean the machine learning. So
Yeah.
in machine learning, the X and Y generally it's non-convex with regards to the to the real data. So, but here I think your XT is required to be convex to data, right? But the XT here is simply the learner. But in my understanding, it seems that your approach cannot be applied to real machine learning problem, right? Because the real machine learning problem, we understand XT as some subtlety of the neural network, and it is non-convex with regard to the data point, right?
Yes. Our method only holds for convex functions. Yeah, but we know the some deep neural network optimization is actually a non-convex problem, and but there is recently some research about the it's called convex to non-convex conversion. If I'm correct, it can be although I do not read these papers very carefully, maybe that means that some convex optimization techniques can be used for non-convex optimization somehow.
I see. And actually, the loss function in machine learning is also convex with regards to the learner. I mean, so maybe in the NTK theory, we can see the network functions or the base learner is a convex. I mean, it's a linear approximation to its initialization at the Gaussian process, right? So maybe it can be applicable in some way.
Yes, I agree.
But here, oh, I see. Okay, thank you.
Okay, thank you for the question.
Okay, if there is no further questions, let's just thank Yuhu again for his nice talk and for the fruitful discussions. Okay, if you have any other questions, just contact Yuhu through his homepage, or you can see the announcement in the Doorkeeper. Okay, thank you all.